Welcome to the lecture series on soft computing in computer science. This session we are going to see about neural network part 2. Under part 2 we are going to see some advanced kind of neural network, that means some kind of neural network that have been never touched in our previous sessions. In our previous sessions we have discussed about primitive neural networks, feed forward neural network, that means a shallow neural network, and deep neural network. So these are all the networks that we have discussed. Of course, present day researchers all have been widely using the deep neural network both in the form of processing the images, text, and so many models are there in the umbrella of deep learning. However, there are other parts of neural networks are also available, and still it gains a lot of momentum among the researchers. So in the topic of soft computing, there are some unexplored neural networks are there, and this session is going to cover those neural networks. First network is going to be the network that dealt with associative memory, and the neural networks in this category or that follows this kind of category are called associative memory neural network. So before getting into it, first let me discuss about what is associative memory. Associative memory neural networks are group of networks that performs the task of pattern association. So you need to know what is pattern association. We are very familiar with pattern classification, pattern clustering, but we are not familiar with what is pattern association. So how the patterns are associated with one another. So in that angle we need to discuss about what is associative memory networks. AMN, associative memory networks, may be either a feed forward kind of architecture or a recurrent architecture. During the training, a AMN may either take a feed forward or a recurrent architecture. This AMN is provided with input output vector pair S.T called pattern, and the weights are updated in a manner that the AMN stores a set of patterns as memories. During testing, the AMN is provided with a key pattern. It responds by producing one of the stored patterns which closely resembles or relates to the key pattern. Thus, recall is made during testing with the help of a information memorized during training. Of course, this is what happened our regular classroom kind of learning, right? Thus, recall is made during testing by the information memorized during training, right? So content addressable memory CAM, address addressable memory AAM. So these are all the two memory neural network that got inspiration from the behavior of human memory. Example for an AMN. See, any pattern that can be dealt as an associated pattern that are similar, contrary, in close proximity or succession. If you could see that this is an image that treated as a noisy image. Why it is noisy? Because the stored image is 3, and if you could see that it may be either 3 or it may be either 8, or sometimes it may be 1. But the image here get distorted, and we have to check what kind of image is. Since the distortion is here, definitely it won't be 1. It may be either one of this, but how to know one of this? See, associative recall retrieve, it is a kind of task that evoke associated patterns, recall a pattern by part of it, recall with a noisy example. Hence, an AMN with the recall stored a pattern by a noisy input pattern by using weights that capture the association. So that is the major role played here, weights. So whenever you want to discuss AMN, so AMN will recall, which means it gets stored the pattern. The stored patterns will get recalled either by means of a noisy pattern or a good pattern, but whatever it is, the weights associated with this plays a key role while recollecting the pattern. So this is what the particular example of AMN. What are the various categories under AMN? Auto-associative memory network, hetero-associative memory network, bidirectional associative memory, and half-filled. These are all the 4 different kinds of auto-associative memory based neural network. The first kind, auto-associative neural network. As I said earlier, whenever you want to study any neural network model, the first thing that you should remember is what is the architecture of that model, followed by architecture of the model, that you should know about what is the equation that are responsible for the execution of that model. Equation may be in the form of maybe in the terms of weight updation, because the weights only plays a vital role in almost all the categories of neural network, and AMN is also not an exceptional. Here the recall pattern, that is the most important one, that is based on only the weights, right. So the weight updation equation. In addition to that, how the net input calculation is calculated, how the output is produced, followed by weight updation, these equations. So the architecture as well as these 3 kind of equations are most essential to study the neural network. See here, the architecture is a feed forward neural network that uses either Hebb rule or outer products rule. And if you want to train this neural network, see the training input as well as the target input same, S equal to T. That means what is the input that you have given in the input side, the same data vectors also can be given in the output side. Now what has to happen, both the input is and the outputs are mapped in general during the training of the neural network, but here in this case input is also the same value, output is also the same value. So during the training, that means during the establishment of the relationship between the input layer as well as the output layer, the entire pattern being the same in both input and output, it gets stored, and the stored pattern is treated as a memory. So that is what the thing. So by the names of auto-associative, the values in the input layer, the values in the output layer are one and the same. So this is what auto-associative network. Now coming to the next network, that is hetero-associative network. Here this network is also going to use a feed forward neural network either by means of Hebb rule or by means of product rule. But here this S is not equal to T. So this you should remember, S is not equal to T. So in this case what you have to think about is the hetero. So the same way what that AMN or AMN based auto associated neural networks is doing, the same way here these hetero associated, but the thing is input you have a set of values and in the output you have a different set of values. So that you should remember, input you have a set of values and output you have a different set of values. So based on that you should think about that. So what is auto associative and what is hetero associative? So whatever it is, the data plays the vital role. So once the data is provided, so based on the data you should understand what are all the input variables, and based on the number of input variables you decide the number of nodes in the input layer, and based on the data you have to decide the output variable, and based on the output variable you have to decide the number of nodes in the output layer. But here in the auto associative, both the, if you have 13 inputs, say for example if you have 13 inputs in the data, so you have 30 nodes in the input layer, the same 13 nodes should be present in the output layer, because we are going to delete both the variable. But in the hetero associative it is not the case. And what is bidirectional? What is bidirectional? So this is two-way, like a recurrent model, this is a two-way. It is also a hetero associative, but it is a kind of two-directional network. It means it performs both the forward as well as backward kind of searches. In the forward side some kind of searches, as well as in the backward side for the stored patterns in the, during the recall process. During the recall process, that system has to take the stored pattern from the set of things. So either it use Hebb rule or outer product rule like the associative memory in general, but it uses the searching in two direction. One is in the forward direction, another in the forward direction. Accordingly, there are two kinds of network, that is continuous and discrete network. And finally, half-filled network, and this half-filled network is a auto-associative fully connected single layer feedback network. Here only the changes, feedback network half-filled. Here also you have two types based on the input values, either continuous value and discrete value. So this is the full list of AMN network. So again, once again I am repeating. So in the under the AMN category you have two networks, one is auto associative heteroassociative, bidirectional and half-filled network. So accordingly we can have a discussion. In general, what is the training algorithm for AMN? Either you can use a Hebb rule or you can use a outer product. So Hebb rule we have already seen in our previous presentation. Let me come to the outer product rule, how the outer product rule has been applied for the auto-associative memory neural network, or in general associative memory network, So let us take an input. So now what is the input? Inputs are S1, S2, S3, etc. What is output? T. So S1, S2 is depends on source. This is a source. T is called by the name targets. T1, T2. For each and every source we have a target. If you want to do a outer product, so these two are vectors, vector 1 and vector 2. If you do vector, the first vector should be transposed followed by the next vector. See, this vector is transposed, that is row is converted into columns, and here it is made as such, then you have to make this rule. So now you have got a matrix of n cross m. See, this is n cross 1 matrix and this is 1 cross m matrix, right, and finally you got a n cross m matrix. So this is what the outer product rule is saying about. You have input and the input is designated as S, and you have output, that output is designated as T. S stands for source and T stands for target. Now you have to take a product with respect to the target, right. So what is that? What is that formula? You have to take the target S to the power T, that is transport and T. So that is what you have to do. So this S is matrix size is n and this is m, and the final matrix is n cross m. So this is what the matrix we have taken. So this is the general principles of outer product rule training algorithm, and the weight updation process is this. So old weight equal to new weight. So that is the process, right. So that new weight Wij, each Wij is nothing but summation of p equal to 1 to p, small p is equal to 1 to p, number of patterns, p stands for number of patterns, SIT p of t and Tj of p of t. See, for each pattern, ST for each pattern, right, and T of p for each pattern. So this is what the system is telling about, right. So this is the idea. You may say here instead of I here for each, but you can say like that, each sample Ti, Tj. Like. So this is that a training algorithm for AMN. Almost all the AMN networks, auto-associative network, hetero-associative network, bidirectional associative network, half-filled network, almost all associative networks are following this principle if you use outer product rule. Because if you could see that, see it outer product rule, and this is C outer product rule, outer product. So the architecture is feed forward neural network. The rule can be either Hebb rule or outer product rule. But with respect to auto associative, you have a single feedback connection, and it is little different when compared with other kind of neural network. BAM architecture, bidirectional associative memory architecture. See the direction, here also arrow network, here also arrow network. So this is the most important one. If you could see that, you may say that this is a 2-layer network and it is a feed forward network, and you may treat that as a kind of a model like Madeline model. So there is a network we have seen Madeline, that you can see that, or you can say that feed forward neural network. So that is shallow neural network. So that thing you can decide. But if you closely watch that, there is a backward arrow here. So this X layer is nothing but input layer, and this Y layer is nothing but output layer, and here you will give the set of inputs, the same thing we are giving the outputs here. So now this memory. For each layer as usual we may get a W1. What is this W11? It is from X1 to Y1. What is this Wi1? It is from Xi to Y1. What is this Wn1? It is from Xn to Y2. So we have these too much of network and we have this too much of network. This is the source and this is the target. So since it is having a finality, we have to take a outer product rule like that, simply by means of a Hebb rule. So this is the architecture is very simple, and the training algorithm is little trickier when you use outer product rule, and very comfortable when you use Hebb rule. But outer product rule plays the most important prominent role because it is a specific rule with respect to associative memory. See, weight matrix calculation. So how the weight matrix is calculated, because weight matrix plays the vital role. This the major purpose of this neural network is the recalling behavior, When this neural network is do the recalling behavior, this recalling behavior is only based on the weight updation process. Based on the weight updation process, the recalling behavior has been calculated, and this is the formula that is used for weight updation. And what is the activation function? So you are asked to recall what is activation function and how this activation function is used and how what kind of role this activation function is playing. Accordingly, these things are there. See, there are two things. One is discrete BAM, another one is continuous BAM. Because why these two types of algorithms are there, discrete, continuous? Because when you dealt with data, there are some variables which may have real values, there are some values which may have whole numbers. So accordingly we divide as the discrete as well as continuous. For if your data contains only discrete numbers, so what kind of activation I can use? I can use either binary or bipolar inputs. Accordingly, in the X layer, the net input j, y in j, how it is calculated? It is 1, yj 0. If this y in j is greater than 0, it is 1. If it is equal to 0, then it is the same. If it is less than 0, it is 0. Likewise, y in j for the bipolar. Bipolar category, you may have -1 instead of 0 and we have, and the threshold values are some theta bipolar. The same thing for the X layer also, f x in j, because why it is f x in j? Because the x in j is here also, the network arrow is from here and here, see arrows are here. So now we have to calculate the total net input in the x as well as the total net input in the y. If you recall our previous presentation with respect to the learning algorithms of a neural network, you can very well identify what is meant by net input. Now after identifying the activation functions, if the variable is a continuous variable or if the value is a continuous value of a particular variable in your data, so what kind of BAM algorithm I can go for? I can go for a continuous BAM algorithm, for which you can use either logistic sigmoid, both for the binary as well as bipolar inputs. So what is this logistic sigmoid is telling? This is the expressions for logistic sigmoid, the 1 by 1 plus e to the power minus y in j. So this is what the activation functions for logistic sigmoid. So that function has been used as an activation function when you find a variable that is of continuous in nature. BAM testing algorithm. So in BAM testing algorithm, first thing you start with this, you have to initialize the weights. After initializing the weights, you have to initialize all activations to 0, So that you should remember. In the previous case, this set of p vectors initialization, maybe you can start with some random values or you can start with some small possible values. Over the period of training you can adjust the weight values and all, but here small change you have to assign with a set of p vectors, right, and present the testing input to the X layer and input to the Y layer. Now what you have to do, you have to update the activation units both in the Yth layer and as well as in the Xth layer. First you have to calculate the net input and complete the activation and send the signal to the X layer. So in the Y node you are more inputs are following, so you have to calculate the net input. Net input nothing but the product of sum of weight values with the input xi, wij. Over that you need to apply the activation functions, that is over that you have to apply that over the net input you have to apply the activation. Now you send the signal to X layer. So X is now here, in that X you have the values, right. Now I have to calculate the functions for this value, for which net input calculation, application of activation functions as well as sending the signal to the X layer, right, sending the signals to the Y layer. So now this go forward, go backward, go forward, go backward. See, this is two things happening. While this process is happening, ultimately what has happened is the memory is stored, a kind of memory is stored, the kind of behavior of the pattern has been stored in the network. So if the activation vectors x and y have reached the equilibrium, so when this process has to be started, x is doing the net input calculation and applying the activation functions, sending the signal to the X layer and Y layer, and Y is doing the net input calculations, following the activation functions and sending to the X layer. So X and Y are doing the same process and sending back to each other. When this process is when it reaches the equilibrium, there are no more data to send from y to x and x to y. If there are no more data understanding or the data relationship has been available to send from x to y and y to x, it means that your system enters into a equilibrium state, and that state is the one which is meant by the halting criteria of the training of the BAM network. The next architecture is half-filled architecture. Under the half-filled architecture, you have the thing, there is a backward connection that you should remember. See, x is there are inputs, right, and there is out. So, this under this way you have what is that? You have a feed forward connection. And if you look at the weight value, see, weight value where it has been taken, it has been taken from this node as an output, and this weight value is fed to other node network. So, this is the small feedback connection. See, weight is taken. So, that means this y1 here. So, what is this? Here also y1. This y2 here. What is this? Here also y2. What is this yy? This is y. So, in a circle, if you could remember, in a circle, I am giving x, and I am going to take y, and this y, if I draw a line here also, this is also going to be y, right. So, this is input and this portion is output, and this y is fed back to the neighboring network. See, in all the cases, for this case network is giving like that. So, this you should remember, and this is the complicated architecture of giving the connection, giving the weight values to one another. So, this is the half-filled network. Under this half-filled network, what is this half-filled model is telling to us? It is an auto-associative, fully interconnected single layer feedback network. It consists of processing elements with two outputs, one inverting and other non-inverting. Two outputs, there are two outputs, one is inverting, another one is non-inverting. That is what I am saying. So, two output, this is one output and this is another output. This is non-inverting output and this is inverting. Inverting means it is giving feedback, it is giving fed to the neighboring. So, this is called inverting, one is inverting and non-inverting. The outputs from each processing element are fed back to the input of other processing element, but now see, that is, there is no self loop. So, this is not self loop, here there is no self loop, this you should keep remember, right, in the architecture. The outputs from each processing element are fed back to the input of the other processing element, but not to the itself. That is the most important thing, that is the most important thing. The network has symmetrical weights with no self connections, yes. So, the network has symmetrical weights with no, again that is the same thing, the W11, W, see this is there is no W11, there is no W22, there is no WII, there is no WNN. So, with no self connections, and these self connections are treated as 0, see WII 0. Accordingly, WJ, WJ both are equal. So, Wij is equal to Wji, both are equal. So, this is the characteristics understanding of the half-filled model. What is the training algorithm? As I said already, the training algorithm is nothing but the weight updation. The first thing is net input calculation. Over the net input calculation, applying the activation function to produce the output. Once the output has been produced, that output has been compared with the target. Based on the error, the weights are updated. So, in general, the training is nothing but weight updation process, and you should always think about how the weight updation process has been carried out. So, during the training of a half-filled network, only one unit updates its activation function at a time. Each unit is found to continuously receive an external signal along with the signal it receives from the other unit. Yes, of course, it has its own inputs, but continuously it is also trying to get the output, that is input from that is treated as the output of the neighboring neuron, and it performs a sequential asynchronous updation. That is very important. It performs a sequential asynchronous updation if and only no new inputs are available, and the updated response are produced and the network reaches the equilibrium. See, updated, see wherever the updation is carried out, the updated responses are keep on updated and they keep on overwritten with the previous pattern, and at one point of time you may find that there is no more data available to send from x to y and y to x. At that stage the equilibrium stage is reached, at that stage you have to stop, right. So, how this weight updation has been carried out? This is the weight updation equation for the binary input, and this is the weight adaptation equation for bipolar input, right. So, Wij is equal to summation small p equal to 1 to capital P 2Si of p minus 1 2Sj of p minus 1 for I not equal to j, because there is no self loop. Likewise, for I not equal to j, Wij equal to, so this 2, this value is been removed, Si p and Si, because this is binary input, you have two different things, and here in the bipolar, so only the direction is changing and you do not have two different inputs, only the direction is changing, one is in the positive side plus 1, another in the negative side the negative 1. So, it is Si of p and Sj of p. So, this is the idea inside the Hopfield training algorithm, right. Now, the energy functions. So, energy function is one which gives how long or how much time the memory is resistant, or memory is having the capacity to store the pattern, how much time the data is available, because it is a memory network, right. So, stability analysis, how the network is stable. So, this is very important. So, the energy function as well as the storage capacity is very essential. If the energy is drained down, there is no memory. Of course, our mobile phone is also the same case. If your battery is down, there is no need to, there is no provision for you to look in the data into the mobile, right. As well as the storage capacity. See, your mobile capacity is also depending on the RAM as well as the external hard disk capacity available. Accordingly, you can store photos or videos and all. So, that is the energy function as well as. For a BAM network, that is the category of network. What are those category of network? Auto-associative network, hetero-associative network, and bidirectional associative network. For all these kind of network, the energy function is 1 by 2 X transpose, W transpose and Y. The minus 1 by 2 Y transpose Wx. But for Hopfield network, the expression is like this: summation I equal to 1 to n and summation j equal to 1 and j not equal to 1 to n yi yj wij minus summation I equal to 1 to n xi yi plus summation I equal to 1 to n theta I yi. This is for Hopfield network. See how complicated these Hopfield network, because of the presence of feedback connection, because of the presence of the connections between the neighboring nodes. So, for a BAM network, the memory capacity is nothing but it is calculated in the terms of C equal to min of m comma n, where m is the number of units in the yth layer and n is the number of units in the xth layer. So, this is for the BAM network. For Hopfield network, the C equal to 0.15 n, where n is the number of neurons in the network. So, this thing you should remember. How the memory capacity of a BAM network as well as a Hopfield network is known. So, the memory capacity of a Hopfield network is directly proportional to the number of neurons totally in the network, whereas BAM network it depends on, it is also depends on the number of neurons, but it should be taken in the aspect that if you have a number of neurons and the number of neurons in the output node and the input node, there is a comparison between how many number of nodes in the input and how many numbers of input, accordingly you should decide, and it should be minimum of m comma n. So, that is what that you should decide with respect to BAM and Hopfield network, and these two parameters are most important parameter. These two parameters are not available with any other network. With this, the idea behind the memory based neural network is come to an end, and you have understood the four kinds of networks. In the subsequent session, we have been dealt with unsupervised neural network model.